My name is Maksym from former School of Agriculture, Social Economics, and SEEP. My co-authors are Fiona Gibson and David Pennell, who made an excuse not to come. And the topic is spatial targeting of ecological restoration in fragmented landscape. And this work was done within National Environmental Resource Program NERP Environmental Decision Hub several years ago. Okay, so please, so this is recorded, it will be posted on, but if you want to ask question, please ask question, and I would appreciate any feedback. So general background that habitat loss is one of the major causes of biodiversity decline, and there are a number of ways you can prevent or stop this. One is you can do more conservation, but if there is nothing more to conserve and landscape is highly degraded, you can do ecological restoration. And governments spend a lot of money on ecological restoration. And obviously there are limited resources, so we want to do this to get most of the benefit with a limited cost. And we need to revegetate or do ecological restoration in places which has greatest ecological benefit and at the lowest cost. And that could be done using spatial optimization, like in this paper which we did with other co-authors. So there are many other examples there are a lot of examples of conservation, spatial optimization and conservation, not that many of ecological restoration, but there are some. The problem with this approach is that suppose so habitat quality is dependent on spatial contact if you're looking at habitat quality for species. So you can do same, it depends on existing habitat context and also on your planned ecological restoration. So if there is a public land, you can plan and you can implement as you wish, and you'll get this result. But suppose there are private owners, and you cannot make them, unless you are in planning economy, or you can use eminent domain, you cannot make landowners to participate. You have to convince them, and suppose someone would not agree to participate in this ecological restoration plan, and then your benefit would not be even close to what you were planning. So answer to this is to use targeting. So if landscape is dominated by private landowners, you can use, or government have to rely on landholders to participate in conservation or restoration, and then we can use targeting to identify certain types of habitats or certain types of landscape or certain cost or certain areas to target ecological restoration with those areas. Targeting could be non-spatial, for example, cost targeting or benefit targeting, if a spatial aspect is not that important, for example, for conservation reserve program. Or it could be spatial, and there is enhanced conservation resource reserve program in the United States when they were targeting water quality from land erosion. For example, you would have some buffer along streams. And not much was done for ecological restoration for biodiversity. And so other issue is that wildlife corridors recently become big buzzword. In Australia, for example, there are such programs like National Wildlife Corridor Plan 2012, and there is Caring for Our Country scheme which used corridors, wildlife corridors, as one of, I guess, elements or criteria to prioritize conservation projects. And this could be viewed as one of the ways to do targeting ecological restoration, spatial targeting. Okay, and then obviously from ecologist point of view, corridors or connectivity is very important and the best thing you can do if you do ecological restoration or conservation. But not much of analysis. There are some reservation about this, but still this is the way to go. But if we are talking about landscape which is with a lot of or dominated by private owners, and when you take into account cost, it might be not the best approach. So in this study we wanted, and then, okay, you can see that there are different plans or ideas, grand ideas to do corridors in continental scale, and it's big kind of flag to, I guess, encourage investment in conservation. And it's in Australia, specifically in Western Australia, there is this Gondwana link plan. What we wanted to do is compare this connectivity approach of targeting, spatial targeting of ecological restoration with other potential approaches. So we took this classification of targeting strategies which were applied to conservation, not to reserve selection by Mokhani and other people. And we classified them into connectivity, which is creating link between existing habitat, aggregation, which is enlargement of, so doing ecological restoration next to existing patches, not necessarily trying to connect. Representativeness, which would be find habitat types which are better suitable for species we want to do. For example, some of them are more, I guess, degraded and cleared and more valuable, therefore, and we might want to do ecological restoration in those habitat types without regard to spatial context. And we want to compare what is the implication of using these different strategies if we have actually people in landscape and they are privately owned and they want to do something else, and there is no guarantee that all of them would participate in this ecological restoration. And kind of common sense, I guess, view, if you look at connectivity, if you want to connect several patches of habitat, and there are many landowners, and some of them wouldn't participate, your whole project would fail. While if you have your targeting is a certain buffer around the existing patch, it doesn't matter who will participate, who not, you'll still achieve some result. Okay, so objective of this study is to compare outcomes of ecological restoration on private land in fragmented landscape using different targeting strategies, which I mentioned, plus completely random strategy. And account on landholders' propensity to participate. For example, some landholders might be more willing to participate and some are less. And you try to account for that. Maybe using not perfect, but one of the methods, potential methods. And also look at how this outcome impacted by different landscape characteristics and for different species. And we use simulation. So biodiversity outcome is function of landscape and species characteristic. We use number of breeding pairs of certain species which landscape can support before intervention and after intervention. And propensity of landholders to participate in conservation would depend on private benefit derived from native vegetation. So we had studies which try to estimate what is the benefit, private benefit landholder derive from some amount of native vegetation on his or her property. And we would assume that if additional hectare if this revegetation, which would result in additional hectare or whatever area of native vegetation would have positive benefit to landholder, then this landholder would be more likely to participate in this project. So we would simulate ecological restoration and the alternative targeting strategies, which I mentioned. So there are connectivity, aggregation. Another one would be representativeness and completely random, no strategy. And then we would use result, repeat many times using simulation, and we analyze using regression. So how do we model biodiversity outcome? use approach by Pulaski and other people who did this in this modeling. Actually, they did optimization of, we cannot say ecological restoration, but just modification of landscape to support either biodiversity or economic activity or combination in Oregon. And in their model, number of breeding pairs of species that landscape can support depends on species habitat compatibility. So some of the habitat types are suitable for this species and some are not. And then amount of habitat required for a breeding pair, for example, we have certain amount, which is like suppose 1 hectare or 10 hectares for one breeding pair, and then number of breeding pairs necessary to sustain local population in isolated patch. So if there is, suppose 1 hectare required for one breeding pair and there is only 1 hectare, there would be no viable population in this patch. And ability of species, but if there are, suppose 10 pairs is enough and there is 10 hectare patch, then it would be usable. And ability of species to move between patches. For example, some of the patches isolated could be isolated if they, if two patches, there are 100 meters between them, they could be not considered isolated if species can travel between, but if they are 10 kilometers apart, they would be isolated. And it depends on species' ability to travel. So this is illustration. For example, we have different suitability of habitat. Green would be better suitability of habitat, and yellow would be less suitable for this species. And there is a certain area which breeding pair can would require. And you can see that on bigger patches we have more breeding pairs, and on smaller patches we have less. And then also there is minimum breeding pairs which could minimum area which, or number of breeding pairs which habitat or patch can supposed to support. So, for example, in this case, we have no breeding pairs because it's only one breeding pair could be supported. And then if some isolated patch is close to bigger patch and species could travel, then we could assume that this is suitable for as a habitat for this species. Okay, so and then as far as private benefit, from our modeling of hedonic, a hedonic model of value of native vegetation, we derived, we can predict what is the benefit of additional unit of area of native vegetation in landscape, and from that we would assume that certain landholders would be more likely to participate than others in ecological restoration programs. So our study area is in central Victoria. We selected 14 representative landscapes. Okay, we didn't select them. We just used someone else's. So ecologists were doing modeling of probability of occurrence of woodland-dependent bird species, and they selected for their purpose representative landscape which would be representative in this area, and they would have different proportion of native vegetation, different types of bigger, smaller, I guess, patches, and just roadside vegetation. So there is big variety of vegetation. These squares are 10 by 10 kilometers, and we assume that those would be representative landscape, even use simulation to model our ecological restoration in these landscapes. So we collected data. So for each of those landscapes, we have remnant vegetation. We have vegetation classes, pre-clearance vegetation classes, and we assume that if we do ecological restoration, we would get same vegetation class type, which was pre-clearance. Also, we contacted experts to get suitability of these vegetation types for different species. And we also have data on property boundaries, on sizes of properties from which we can calculate what is existing vegetation on each of the properties and other characteristics which impact property prices or values. Then we created targeting areas in each of those landscapes. So for aggregation, we had just buffer one cell. So we model on the level on 1 hectare cells. Our modeling unit was 1 hectare cell, so we rasterized our data to 1 hectare cells. And we assume that for aggregation, our target area would be cells immediately adjacent to patches. For connectivity, we selected area which would, or belts which would connect existing patches and possibly along the streams or roads. And for representativeness, we selected vegetation types which are suitable for all the species which we will study, of all our, I guess, representative species. And then another strategy would be no targeting random. We selected 5 representative species, and we, from literature and from expert opinion, we got data on area requirement for 1 breeding pair, for dispersal capacity or ability of this species, and for minimum vegetation, minimum viable population in a patch. So representative species would be very different. So, for example, lace monitor would be big lizard, which travel far and require a lot of area. Then there is, on the opposite range, we have this marble gecko, which is very small, require very small area and cannot travel far. Then we have yellow-footed antichews, which is this. Again, small species. We have brush-tailed pascogale, which is kind of flying squirrel, which is bigger species, require bigger area and can travel far away. And we have 1 bird, which is a diamond firetail.
Is that minimum viable population for 1 hectare?
It is how many breeding pairs in a patch in order for them to survive.
So it doesn't.
It's not
doesn't
in.
specify an area for that.
No, we can use this area and this population to calculate what's the minimum patch.
Okay, gotcha.
But it's that if we would assume that patch is completely isolated, but then if we would do adjustment on the connectivity of landscape. So depending on how far species can travel, we could recalculate, do adjustment of this number of breeding pairs which can be supported by this species, by this landscape. Okay, and so what we do simulation. We repeat 20 times. We assign, so within our targeting areas, we pick pixels to revegetate. We have 4 different targeting strategies within our budget, either 10 hectare or 30 hectare or 100 hectares in each of the landscapes. And we use 2 approaches to pick those pixels. One is completely random, assuming that we don't know nothing about propensity of landowners to participate. Another one is using private benefit. So the higher, it's also random, but it's adjusted. The probability is adjusted by this private benefit which landholder would derive from the additional hectare of native vegetation. And then this private benefit would change, so the first hectare would be bigger. And then once we do this, we recalculate this private benefit and do it again. So we allocate using this random strategy, is a random completely or proportional to private benefit. We allocate our ecological restoration to these 14 landscapes, and then we calculate biodiversity outcome, which is how many breeding pairs can this landscape support in each case. And then we collect this data and calculate difference between biodiversity outcome in landscape before treatment and after treatment, and then we do statistical analysis of the results. Any questions?
How do you take into account predator prey in your...
No, we don't take that into account.
What couple of demo numbers?
So this is a result of our regression. So we did analysis separately for each of the species. So this is generated data from our simulation. Intercept, that's not interesting. Oh, okay, and the dependent variable would be log of change of number of breeding pairs. Okay, and the explanatory variable would be, there are 3 dummies for our targeting strategies, and they would tell what is the difference with a completely random strategy. Okay, so base is random. You don't do any targeting, and then if you do aggregation, connectivity, representative, this coefficient would tell by how much, by what percentage our outcome is better than random, than no targeting. Okay. Then there is private benefit, so whether we use this private benefit or not. So base level is no private benefit, just random. I mean, assignment to landowners within targeting, and if private benefits, then we take into account that those who get private benefit would be more likely to participating. And then we'll take log of budget, which is like how much can we revegetate, and then log of area of native vegetation in a landscape. That's characteristic of a landscape. And then we tried also to take into account what is the fragmentation of a landscape. And we use Shannon index for that. It's probably not perfect measure, but and also it was not significant anyway. So let's go to strategies and species. That's something which we're interested to look. So you can see that in most of species, aggregation would shown better results than connectivity. Contrary to what ecologists would say. So for brush-tail pascagale, for diamond firetail, for lace monitor, and for yellow-footed antichinus, aggregation would so using aggregation strategy would result in better improvement of outcomes than in connectivity strategies. And obviously the explanation of that is that for connectivity you often would actually not succeed in achieving connectivity. And then representativeness would have lowest, I guess, improvement compared to completely no strategy. And the only exception is that for a marbled gecko, which is very small species, require very small area, 400 square meters, we have worst result for aggregation. We have no difference with connectivity, and have better result with representativeness. And the reason is that, so because of our modeling scale, we have 1 hectare units of like additional ecological restoration. So basically, when we put a 1 hectare patch, it's already enough to support population. It doesn't matter whether there is connectivity or not. But if we use the representativeness every time you get into the vegetation type which is suitable for this species, and if you do aggregation, sometimes it probably would not be the best, and it will be even worse than if you just do completely random. It's just basically an artifact of our species. Again, our modeling strategy and species size. Okay, if you look at private benefits, you can say that for some species, for 2 species, diamond firetail and yellow-footed antichus, which are kind of medium-sized species, we have better outcome if you take into account private benefit. When we take into account that those landholders who get private benefit from ecological restoration more likely to participate. The thing is that in this case, private benefit of landholders are positively correlated with, I guess, species preferences. So for marbled gecko, we also had a little bit of positive impact. For lace monitor, we have no impact. The thing is that there's a big species. They travel very far. They have really big requirement. So it doesn't matter, basically, for where do we put, whether it would be landholders, those who prefer get private benefit or not. And obviously, log of the budget, it's just elasticity of our, it's the main variable which drives ecological restoration. And also we can say that the more native vegetation in landscapes, the greater benefit we get. except that marble gecko, which I told is very small, it doesn't matter. So for marble gecko, because of our scale of modeling, it doesn't matter what existing vegetation is or whatever. One patch is enough, at least in our model. Any questions?
When you say that while the estimates for aggregation are all largely higher than connectivity, and they're both different from random,
Yes.
are they different from each other?
Okay, so we could measure, but you don't see here. If you look at errors, we could say that here they are different. Obviously, here they are different, here they are different, and I cannot tell about this. But you suggest it would be useful to also put.
Well, just at least to know whether
Yeah. Okay.
aggregation is.
Good suggestion.
Yeah, we can't see the standard errors up there, so we can't
Yeah.
make a rough calculation.
Okay. Thank you.
And I have a question. How did you decide the buffer for the aggregation?
For aggregation, it's just one cell buffer.
So 1 hectare.
Yes, it's 100 meters. And for representative, it's just one cell corridor, and preferably through existing kind of very small patches, maybe along the streams or along the roads. So it was done manually. So for aggregation, buffer was done automatically, and for connectivity, it was manually. And for representative, it's also automatically using the vegetation type, so it's suitable for all of the species. Conclusion: the effectiveness of strategies depending on species, and also restoration with connectivity isn't best. So best would be, for most of species, would be aggregation. And accounting for private benefit is make different for some of the species. Okay, so this acknowledgement to NERP, Environmental Decision Hub, SEED, INFA, North Central CMA, who provide us some expert opinion.